Um, all right, so we're having this class online only today, although I guess Friday's class was online only too, technically, since everyone who came was online then as well. In Friday's class, we completed the previous unit, which was, I guess, unit 10, which was on enthalpy, basically, ways of determining enthalpy for reactions and processes and things like that. We talked about how you could use enthalpies of formation. We talked about how you could use bond enthalpies, and we talked about how you can use calorimetry to actually measure delta H's for reactions. One thing I also mentioned on Friday, which I looked a little bit more into, was for those of you who are actually like in Wolfville or nearby that can attend in person, what I'm trying to do is set up a couple of what I'm going to call mini labs. These will be short labs that take about the same amount of time that we have in one of our classes, and line them up for sometime later in the semester. The idea here is, if you're able to come, great. If you can't, if you're, living somewhere else, that's fine too. You don't have to. There's sort of more an enrichment opportunity than anything else. It will not contribute to your grade, so it's not like you're missing an important part of your score for the course. But for those of you that are here, I think, it's kind of sad for me that we don't have live in-person labs, because I feel like that's important in chemistry. And I hope to just give you a little bit of a flavor of that and maybe try to pepper a few in as we go. So I'm trying to line that up with a few of the other profs to make that work out well. Another thought was to maybe give you a tour of the A lab, which is in the pavilion, which is next to Elliott Hall, which is an analytical chemistry facility. I think that might be another thing we could throw in for enrichment. So I think we're going through the material well. I'm not overly concerned with us not covering the material and taking class time to do some labs. I think that might be more valuable use of time for those of us that are present. If you have strong feelings about that, please let me know. But what I'll probably be doing is at some point putting up a poll on Acorn asking who is actually available for something like that, and who's not, right? You can figure something out. Quiz is going on this week. Don't forget to complete that by Friday. Yeah, you don't have any lab gear. You don't have to worry about buying anything. Anything you'll need will be provided. Yeah, the quiz, a few of you have already completed the quiz. The grades are looking very good so far. So just don't forget that closes at 5 p.m. on Friday. So make sure you find time before then to complete that. And that's 5 p.m. Atlantic time. So if you're in a different time zone, you have to factor that in as well. Assignment 2 seems to be going smoothly. It'll be due Tuesday evening, and assignment 3 will follow it up before too long. No major issues there, it seems so far. Things are going pretty smooth. And what we're going to do today is start our next unit, which is called Spontaneity. And we're going to define what that means and how we can think about a reaction in this context. So I guess first of all, I need to define what a spontaneous process is. And a spontaneous process is just a process that will happen all on its own without any input of energy or effort or organization. And my example here is a skier. I mean, not to say there's no effort or anything involved with skiing, but if you have skis on and you're at the top of the hill and you point yourself down, gravity will just take over and pull you down the hill. You don't have to work to move towards the bottom of the hill. Whereas the opposite process, which is going up the hill, is not a spontaneous process. You can't just stand at the bottom and expect to, with no input of energy, just go up the side of the hill. And so in order to get back up, we use a chairlift, and that of course requires energy to get you back up. So for the most part in chemistry, when we have a spontaneous process, it's one that will happen without you putting any energy into that process. But the reverse process is typically, well, it is by definition non-spontaneous. It doesn't mean you can't make the reverse process happen. It just means you're going to have to modify the system in a way that the reverse process either becomes spontaneous or you put energy in to make that non-spontaneous process happen. And so the example I have here is a car rusting. You know, if you take a car and you know, leave it out in the field, eventually it'll react with the oxygen in the air. The spontaneity, by the way, if a reaction is spontaneous or not spontaneous, it tells you absolutely nothing about how fast that reaction is. That this is a totally different concept from rates and kinetics. So this process of the car rusting is actually a very slow process that would take place on the order of years, but it will eventually take place. It will eventually happen. So in terms of what makes a reaction spontaneous and non-spontaneous, what we do observe is that many times when you have a reaction that's exothermic, those reactions are often spontaneous reactions once the reaction is initiated. So I have here the reaction of wax with oxygen burning to make CO2 and water. And that's a spontaneous reaction, but only after you light the candle. And so the thinking here is that this reaction requires some activation energy to get you over the barrier. But once you get over that barrier, the reaction is exothermic. It gives off excess energy in the form of heat. There's a negative delta H. And it's that heat that's given off that serves as the activation energy for the next molecule of wax that wants to react. So it becomes self-sustaining once you initiate it, because each reaction is providing the energy necessary, the activation energy for the next molecule over. So this is true for many exothermic reactions. Once you get them started, they'll just proceed on their own. And I guess you could say, I mean, it's happening with an input of energy, but the energy is coming from within the system itself. So it's not absorbing any energy from its surroundings. However, some endothermic processes are also spontaneous. So this reaction is an example of a mix of barium hydroxide, which is a solid, and ammonium nitrate, which is also a solid. And if you mix these two together, and just these two solids, and you stir the two solids, what happens is a spontaneous reaction that is shown the balanced equation on this slide. And this is an endothermic reaction, so the mixture actually gets very cold. And this is just a demo where you can see there's a little bit of water spilled on that block of wood. And when you set the beaker on top, the reaction will get cold enough that it'll freeze that water. And once it freezes the glass to the wood, it'll stick, like you see right there. So this process is certainly spontaneous as well, once you mix them together. And it's actually an unusual example of a reaction where two solids react with each other. Normally, solids will not react unless you maybe grind them or put them under very high pressures. So what we see then is sometimes exothermic reactions are spontaneous, sometimes endothermic reactions are spontaneous. So clearly, you know, if a reaction is just exothermic or endothermic, that's not enough to know if it's going to be spontaneous or not. There's more to it than just whether it's endothermic or exothermic. Another thing I'll draw your attention to is, imagine you have a glass of water with ice cubes inside, and if you just leave this out on the table at room temperature, what will happen is the ice will spontaneously melt, and eventually the ice cubes will disappear and you'll have nothing in there except a glass of water. And this is a spontaneous process. However, if you cool this down and put it in the freezer, the reverse process becomes spontaneous, meaning the liquid converting to the solid becomes a spontaneous process. So whether or not a chemical process is going to be spontaneous will depend also on the temperature that you're at. Sometimes a process is only spontaneous at certain temperatures, and it becomes non-spontaneous at other temperatures. And the reverse can become spontaneous. like we see in this example. Okay, I'm gonna just shut my email down here because it dings every time I get one. Great. So, scientists, physical chemists determined what this sort of extra piece is that relies on temperature, is not related to whether it's exothermic or endothermic, but does factor in to whether a reaction becomes spontaneous or not. It's probably one of the most enigmatic terms in all of chemistry. It's one of the most difficult ones to define, and it's one of the ones that has the most, I would say, bad explanations or incorrect explanations available out there. And it's called entropy, and it's a thing that's not well understood. If you learned about entropy before in high school, you might have heard it defined as a measure of the disorder of a reaction. That's not, it's not really what it is, and it's also not really considered to be a good explanation or definition of what entropy is. And the reason for that is because disorder is not something you can really quantify or measure, where entropy definitely is. Whether something is ordered or disordered is maybe a matter of opinion, and entropy is not a matter of opinion. It's a physical reality, and a better definition, and the way this is officially defined, is it's a measure of the number of microstates within a system. And a microstate is just a way of arranging the system in terms of the molecules' positions and their energies. So there's actually a definition that you can calculate the absolute entropy of a system, where the entropy is equal to Kb, which is called the Boltzmann constant. So this doesn't change, and the number you can see is there, times the natural log of W, where W is the number of ways of arranging all of the molecules and the energies within that system. Now, the Kb part's easy. The W part is an extremely difficult value to actually predict or measure for a chemical reaction. So this equation, while it's important because it does relate the entropy of a system to these microstates I'm talking about, this equation is rarely used because it's not like you can just go count microstates for a system. It's a very involved process. All right, so entropy is related to the number of ways of organizing the system, and it's proportional to the natural log of W. So what this actually means then, think about it like this. Imagine you're on a staircase and you are walking up. And let's say the staircase has, I don't know, let's say 20 steps. If you have 20 steps, you could potentially be on any one of those 20 steps. So what we could say is there are 20 microstates in this system available to you. You could be on any one of those 20 steps. You can't be halfway in between one step and the other step. You're in one of these 20 spaces. So we would say there's maybe 20 microstates in that system. If you take a longer staircase, and this is the longest staircase in the world, it has 11,674 steps. Then there's many, many more microstates available. And we would say that the entropy of this system is higher because there's more ways within this system that you can arrange your position, and I guess by the same token, your potential energy. Imagine if you take this same staircase we have here, and instead of having just one person on the staircase, we have two people on the staircase. Then there's going to be many more than 20 ways of arranging those two people within this system of 20 steps. And so for that reason, we would say that this is, that would be a lot more microstates if you have more people. So this is a very kind of macro level thing. If you think about molecules in a let's say an enclosed container, there's many, many molecules there, right? And there's many, many possible locations, positions, and energies that those particles can occupy. So rather than try to get an absolute measure of entropies of a particular system, what we usually try to do is express it in terms of change associated with either a physical or chemical change, like a delta S. So the entropy change for some system is just whatever the initial entropy was subtracted from the final entropy. And just like we saw for delta H, delta S is also a state function. So what that means is all we care about is what the initial state is and the final state is in some chemical process. We don't care what path was taken to get from the initial to final state. So it simplifies this a lot. And remember when we used Hess's law in the previous unit, what we were able to do using Hess's law was calculate delta H's for reactions because we had heats of formation, we had bond dissociation energies, we had different measures of delta H's for known processes that we could kind of add and subtract together to give you a net chemical equation, which we could use then to predict the delta H of some reaction that we don't already know. That only works because delta H is a state function. The exact same thing is true with delta S. Because it's a state function, we just care about the initial and final states. All right, so let's come back to this idea of microstates and move from the stairs to an actual real chemical situation. So let's look at this container we have on the right. So this is a sort of like a glass bulb, which is filled with some gas, and it's connected by a stopcock to a second bulb, which is evacuated, meaning it's got a vacuum inside. There's no particles inside. What we know will happen if you open up that stopcock, if you twist that little knob and allow the two sides to communicate with each other, what will happen is the gas will rush out of the left-hand side into the right-hand side spontaneously until you have equivalent pressures on both sides. So this is a reaction or maybe a chemical process, expansion into a vacuum, where what's happening is the number of microstates available in the final state in this system to the gas molecules is way higher. Well, it's double what it was when you started out. So, and that's because the volume is increased. There's way more locations where the particles can be found. And so what we find then is that whenever you have a chemical process that causes expansion, so if you expand a gas, like you see here, that will lead to an increase in microstates and therefore an increase in entropy. So we would say for this process, going from the compressed gas to the more spread out gas, that would have a delta S value we would expect to be positive. Positive just meaning it's an increase in entropy for that process. And not surprisingly, if you can imagine this process, it's going to be spontaneous. It's going to happen just on its own. The reverse process would never happen spontaneously. Imagine having the bottom situation, right? Bottom situation that we see kind of here. Imagine all of the gas rushing into just one side. Like that's not going to happen. Here's a few other examples. We have, in this case, we have two blocks of metal equal in size, one heated to a temperature of 100 degrees Celsius, the other at 0 degrees Celsius. And if you stick them to each other, what will happen is thermal energy will flow from one block into the other block. It'll go very conductive towards heat, most metals are. And what will happen is it'll kind of hit an equilibrium where both sides are the same temperature. You'll see 50 degrees and 50 degrees. This is a spontaneous process. Heat will transfer from a hot object to a cold object spontaneously. But what's happened in this case too is an increase in entropy. That what you've done is you've taken a certain amount of thermal energy and you spread it over double the volume. So spreading out matter, which is what we see here, expanding the volume that matter can be found in, increases entropy. but the same is also true for energy. If you can make energy less concentrated and more spread out, that is a positive delta S as well. Here's another example for C. We have a volume of some pure solvent like water. And if you take like a concentrated dye solution, like food coloring, and you put a few drops in, what will happen is it will not stay concentrated in a little drop. It'll diffuse over the entire volume of the solution that's in there. So you can kind of think of this as taking the number of molecules that are present in that drop and spreading them over a much greater volume. So that's another example of a positive delta S. Okay. All of these are physical processes that we're looking at so far. Spreading things out, expanding them, these are all things with positive delta S values. One thing that we know is that if you compare any liquid to the same substance frozen as a solid, the liquid will always have higher entropy than the solid form of the same substance. So if you look at ice melting, like you see in this case, this is a picture of an iceberg, obviously. This process will have positive delta S going from H2O solid to H2O liquid. And this is just anytime you go from solid to liquid, that's going to be an increase of positive delta S. We sometimes call this delta S of fusion, but that's going to be positive number 2. Gases have a much higher entropy than liquids. And this you can think of as because gases take up a much higher volume than liquids do. A big increase in volume. So what we find is that the delta S of vaporization is a very large number, much bigger than 0, so it's always positive. And, you know, I have a picture here of a clothesline, and there's a big increase in entropy for the water molecules going from the liquid state when they dry out and enter the gas phase. Summary: solids have the lowest entropy. We could say it is the most ordered, but maybe a better way of saying that is there's the fewest number of microstates available to the particles when it's in solid form. There's only certain fixed positions that those atoms or molecules can be present in, and there's a limited number of ways of organizing the energy. Going to a liquid form, we could say the number of microstates increases. There's a lot more motion, and so because there's a lot more motion, the particles will have different velocities, and that means they'll have different potential energies. So there's more ways of distributing the energy as well. Gases have the highest, they take up the highest volume. There's more volume for the gas to spread out in, and also there's going to be a greater distribution in terms of velocities for each individual gas particle. So the energy will be, there's more ways of arranging the energy as well. More microstates. So that W increases, you know, as we go from solid to liquid to gas, but we don't really measure W. I don't think I've ever seen a problem where we give you W or ask you to use this equation, but it is something that I think is theoretically calculable, but we won't be doing that. It's not easily measured, that's for sure. Entropy and temperature. So this is just taking some system and just not doing any chemical change, not doing any physical change in the sense of, you know, going through a phase change or anything like that. All we're going to be doing to this system is warming it up. So an example might be you have, you know, a metal block and you warm it up from 10 degrees to 20 degrees, for example. There's no chemical physical change, just a change in temperature. What we find is that the entropy of that system increases as you increase the temperature without doing anything else, temperature change only. And you can kind of think about it in terms of the individual solid particles. That block of metal, right? You can think of it as being all these metal ions in a lattice in 3 dimensions, right? It's like a really bad drawing here. Anyway, we have this 3-dimensional arrangement of these atoms, and those atoms have some motion. It's not like they're perfectly fixed in one spot. They're kind of jiggling around a little bit. They're vibrating, and this little squiggly line is sort of meant to be like what the path of that particle might be over a period of time. What happens when you heat it up is the motion, the vibrational motion of those particles increases. So there's more motion. Because there's more motion, there's more ways of organizing the energy, and that leads to an increase in entropy of that system as well. Great. So raising the temperature increases the entropy. It's another interesting process right here. We have molasses and we have sugar. So when you have sugar cane and you press the liquid out of sugar cane, which contains sugar and it contains a lot of other compounds too, what happens is if you try to purify that liquid, which is done in large refineries, you can boil off a lot of the water and let it crystallize, and you get these brown crystals of sugar, which we call brown sugar. And that brown sugar is mostly sucrose, which is white, but it also contains obviously other substances that are giving it its color. And so we call this brown sugar. What you can do is then dissolve that in water, heat it up, and then let it cool a second time, and you'll get crystals a second time, which is yellow sugar. And then you can do it a third time, and you get white sugar. So this is a successive purification process. So each time the material you're taking off is actually molasses. So there's different grades of molasses. There's fancy molasses, which is I think the common one people use. There's blackstrap molasses is another one. Those are different grades of molasses, are depending on which of these stages of purification of sugar that molasses is coming from. So I think it's the final stage where you get the fancy molasses. And I think it's the beginning stage that you get blackstrap. If anyone's into cooking, then maybe you'll find that interesting. All right, so entropy, we find that pure substances have lower entropy than mixtures. So this process here, going from the darkest to the medium to the white sugar, this is going to be having a negative delta S. There's a decrease in entropy going from the impure to the pure. Pure mixtures, pure substances will always have lower entropy than the mixtures. And what that also means is if you mix two pure substances together and they dissolve, that mixing process will always have a positive delta S. That will always increase. So if you have a cup of coffee, I realize a cup of coffee is not a pure mixture, and you add to that sugar, that process, and then what do you have now? The mix. That process is going to have a positive delta S because you're mixing, I guess, a pure substance into a liquid, and then the mix is going to have a higher entropy. Summary, what are some things that cause an increase in entropy then? Going from solids to liquids, or dissolving a solid into a liquid. Solids or liquids going to gases, big time. Increasing the temperature, just warming something up. Any process that increases the number of molecules of gases, and this is more in chemical reactions that produce gases, but also in phase changes that convert liquids to gases or solids to gases in the case of sublimation. And lastly, we increase the volume of a system. That's expansion. That's going to increase the entropy as well. So let's look at some examples of some processes and see if we can predict whether these are going to have positive or negative delta S values. We're going to start out in the first case with sublimation of dry ice. And you can see we have CO2 solid going to CO2 gas. And I'm going to ask you to put in the chat whether you think that's positive or negative delta S. I should get fancy here. There's ways of like putting polls and stuff in there, but don't care too much. Positive. Good, yeah. So this is positive for sure. Increase in the number of moles of gas. Gas is produced, it's going to be a positive delta S. Sugar cube is dissolved in a cup of coffee. I think we just looked at that exact example. So yeah, that's going to be positive as well, because we're taking a pure substance, which is the sugar, or practically pure, and we're dissolving it into a larger volume. Here's a chemical reaction where we have iron solid plus 1.5 oxygen goes to iron oxide. So this would be rust, right? This would be the process of a piece of iron metal rusting, which we know is spontaneous, but that's not what the question's asking. We don't want to care if it's spontaneous or not. We want to know, is the delta S positive or negative? Any thoughts on this one? Good, we got a couple negatives. Great. That's negative because we are losing moles of gas. Gas is not being produced, it's being consumed. Definitely negative delta S. Last, helium flows from a cylinder at high pressure into a balloon at atmospheric pressure. So this is taking a gas that's under high pressure and expanding it into a larger volume, because the balloon, of course, will accept a larger volume there. So this is, again, a positive delta S process. Great. So this is pretty good. I think, got a pretty good understanding, at least, of, hopefully, what entropy is. If you've studied entropy before, I don't know if this has made things more clear or less clear, but it is definitely a bit of a nebulous concept. And yeah, at least we can hopefully recognize processes that are positive or negative, and we'll soon learn to apply mathematics to this as well. So we already looked at the first law of thermodynamics, and the first law of thermodynamics was just that energy cannot be created or destroyed in a chemical process, or in any process for that matter. So the amount of energy available in the universe is always a constant. You can convert energy from one form to another, but you can't make it appear out of nowhere. The second law of thermodynamics is actually more around entropy. And basically what the second law of thermodynamics says is that the entropy of the universe is always increasing through any spontaneous process. It says that if you look at the change in entropy of the system and include as well the change in entropy of the surroundings for any sort of process, the sum of those has to be a positive value as we move through time. It doesn't mean that both delta S system and delta S surroundings both have to be positive. It just means that if one is negative, the other one has to be positive by a greater amount to offset that is the case. Spontaneous processes increase the entropy of the universe, okay? And so actually the same is true for non-spontaneous processes, because the only way you can make a non-spontaneous process happen is by coupling it with a spontaneous process. So maybe I'll just change this. All processes that happen, right? So, you know, if a process takes place, that process is increasing the entropy of the universe. And so we have to be able to get a handle on the delta S of the system and the delta S of the surroundings to really fully appreciate the delta S of the universe, because we don't measure delta S of the universe. All we do is we measure delta S for systems and surroundings. Add them together, you get for the universe. Okay. So we know then for a spontaneous process that delta S of the system plus delta S of the surrounding, which is delta S of the universe, has to be a value that's positive, somehow greater than 0. When a chemical process is exothermic, what happens is it gives off heat, thermal energy to the surroundings, and the surroundings are absorbing that. So that system is losing energy to the surroundings because the surroundings are gaining energy. They're increasing in temperature. It could cause an expansion. It could cause all sorts of things in the surroundings. An exothermic process will cause the surroundings to have an increase in entropy, always. Every time the surroundings absorb thermal energy, their entropy will increase. So we can actually express this mathematically, and we'll say that the delta S of the surroundings, and this is again assuming the process is only emitting energy in the form of heat, which is an assumption we made at the beginning of the last unit. Remember, we talked about how some reactions can give off energy in the form of light, and maybe some other methods as well. But most of the time, most of the energy is given off in the form of heat. We can say that the delta S of the surroundings of a chemical reaction is just equal to negative of Q of the system, because remember we had Q surround equals negative Q sys, meaning whatever energy is lost by the system is gained by the surroundings. And that's just divided by the temperature. So that's actually a way of measuring the delta S of the surroundings in the chemical process. If T and P is constant throughout the process, we can instead say that delta S surroundings is negative delta H of the system over T as well, because Q sys equals delta H sys at constant pressure. Perfect. So let's look at an example. Calculate the entropy change of the surroundings. So we want delta S of surroundings for the following reaction at 400 K. Okay, and we're given delta H for this particular reaction. So delta S is just equal to, okay, well, first, before we do this, think about first whether the sign of delta S surroundings should be positive or negative. We know this delta H is negative, so it's exothermic, so it's giving off heat to the surroundings. That means the surroundings are absorbing heat, and whenever a system or surroundings absorbs heat, that's going to increase the entropy. So right out of the gate, we're expecting a positive delta S value to come out of this particular question. So delta S surroundings, we can see from our equation on the previous slide, it's just negative delta H system over T. Negative delta H system, negative delta H system over T, which is equal to negative 2044 kilojoules per mole over 400 Kelvin. Notice those negatives will cancel with each other. I just need to bring up, I think I need to bring up something. I've done the math already on another slide here. I just need to get the number. Okay, yeah. So the number that we get when we do the division is positive 5.11 kilojoules per mole K. Or sometimes you might just write that as 5.11 kilojoules per K mole, something like that. That's the units that we always express entropy in. And yeah, so that's good. That allows us to figure out exactly the delta S of the surroundings. Okay, makes sense. It's positive. We have an exothermic reaction. This makes total sense. Now, to determine, by the way, if this process is spontaneous or not, we only have half the puzzle, right? To determine if it's spontaneous, we need to know delta S of universe, which we don't know right away yet from this particular question, because this is equal to the delta S of surrounding plus the delta S of system, and all we've calculated here is the surroundings. So we need to know this other piece to determine if this process is going to be spontaneous or not. So we don't have enough information yet. One thing that we find is that if you have a process that's reversible, so generally what this means is a process that is changing from, it's in an equilibrium state as it's changing. So the most typical example of a reversible chemical change is a phase change, where if you imagine you have, a glass of water that's undergoing process from liquid to solid, it's freezing, it's sitting in your freezer or sitting outside on a day like today. When that water is half frozen, it's in an equilibrium between liquid and solid, and you can add a little bit of heat, and that will push it a little bit more towards the liquid phase, or you could remove a little bit of heat, and that'll push it a little bit towards the solid phase. So we would say this is reversible at all points in time. An example of a process that's not reversible might be like burning a log, where you're producing gas that's escaping the system. It's going up the fireplace flue. You can't really push that back a small amount by adding or subtracting a small amount of energy. So phase changes are examples. There are also chemical change examples of reactions that you can push a little bit forward or a little bit back by adding or removing a small amount of energy. But phase changes are the most common examples that we'll be seeing certainly in this course. So when that's the case, when you have a change that's reversible, we could say that the delta S in that example is just the Q, the amount of heat that's added reversibly, and the temperature divided by the temperature of the system. So this is the delta S of the system here. So here's some examples. These, of course, reversible processes because these are both phase changes. We could say that the delta S of the system for vaporization is equal to the delta H of vaporization over the temperature, the boiling temperature. Same thing, we can say the delta S of fusion is the delta H of fusion over the melting temperature. So this is a great way to figure out delta S, a very simple way to figure out delta S for processes that are reversible like this. You got to be careful though, because you can't apply this to most chemical reactions. You can't just keep going and use these for any kind of chemical process. It only works if the process is reversible, which is the case for things like that. Let's do an example. What is delta S of vaporization for water at its boiling point? So this is not that difficult for water. If you see on the previous slide, we have the equation right here. TB is the boiling point. Delta H of vaporization, I suppose you need that to answer this particular question, is 40.7 kilojoules per mole. And the boiling temperature of water is 100 degrees Celsius, which we always put things in Kelvin here. (109.1 joules per k-mole). Notice in this calculation we changed the units of kilojoules to joules. So really it would be 0.1091 kilojoules per k-mole. Delta S values are often expressed in joules rather than kilojoules, mainly because many chemical processes, the delta S is less than 1 kilojoule, which makes sense then to use the other unit. All right, so we have an easy way of calculating the delta S for a process that's reversible, and this is because it's in this equilibrium situation where basically what's going on in an equilibrium situation is the delta S, or we could say that the delta S of the universe is equal to 0 equals delta S system plus delta S surround, which means the delta S of the system is negative of the delta S surround. So if you look at this equation for delta S, it's the same as the equation we would have for delta S surround, except there's no negative sign anymore. And that's because of this relationship right here. Okay, so what have we learned? We learned today what entropy is. We learned how to look at a process and predict if the entropy change is positive or negative. We learned how to calculate the delta S of surroundings for any process. We can get that from the delta H of the reaction. We learned how to calculate the delta S for the system if it's a reversible process like a phase change. Okay. All of this ties into the second law of thermodynamics, which just states that a spontaneous process will have a positive delta S of the universe. If it's at equilibrium, which is the case at every point in a reversible reaction, then the delta S of the universe is actually equal to 0. It's not the forward nor the reverse reaction is going to be favored. And I think that's a good place to leave this particular topic. We did quite a bit today, and hopefully this maybe is a bit more clear, and we will look at how we can apply some of this stuff as well. So hope you guys are able to have a bit of fun outside in the snow. Hope to go for a snowshoe sometime today, and we'll see you guys on Wednesday.